Hi everybody, this is Dr. Pennington again, and this is another video about Lewis structures. This is actually our third video about Lewis structures. I hope you can see the importance of being able to do these things. And this video is a testament to the unfortunate fact that in chemistry there's more exceptions than there are actual rules. And the octet rule is one of those that does have a bunch of exceptions. We'd seen on previous videos before that in order to have a valid Lewis structure, your atom, unless it's hydrogen, needs to have 8 electrons around it. Well, the fact is there are some exceptions to that, so let's just talk about a couple of those. We can disobey the octet rule by having less than 8 electrons around an atom, and we've seen that for hydrogen already. Also, it occurs for a few other atoms, and it's really only an issue for boron and beryllium. And the reason why these guys are allowed to have an issue with the octet rule is because of their size, because they're too small. You can also have disobeying the octet rule by having more than 8 electrons around an atom, and this is much more common, simply because there are many elements that are very big versus elements that are very small. There really aren't too many of those. Let's just start off and spend a couple of minutes on the exceptions where there are less than 8 electrons around a particular atom. So BF3, boron is in group 3 valence electrons. Fluorine is in group 7, and there's 3 of those, giving us a total of 24 valence electrons. Now, central atom, boron, 1, 2, 3 valence electrons. Fluorine, 1, 2, 3, 4, 5, 6, 7 valence electrons, 1 bond, 3 bonds. Boron's going to be the central atom. So therefore, boron, and I'm just going to put 3 fluorines on here. And I'm going to do my octets of my fluorines first, like so. And in doing so, I've used all the 3 electrons on boron to form bonds. Notice there are no other electrons on boron to be able to do anything. So boron is able to disobey the octet rule by having no more electrons. So this is actually the valid Lewis structure for boron. This does make boron something called a Lewis acid. It can accept electrons from somewhere else and get 8 electrons here. But for right now, all we need to understand is that this is a valid Lewis structure even though there are not 8 electrons around boron. But you can see the fluorines all have 8 electrons around them. When we look at beryllium chloride, beryllium is in group 2, so therefore 2 valence electrons. Chlorine is in group 7, like fluorine, and there's 2 of those. 14 plus 2 is, of course, 16 valence electrons. Beryllium, 2 bonds. Chlorine is exactly like fluorine, 1 bond. So beryllium central. So it's not too much of a stretch to see, well, this is what beryllium chloride looks like. And in the same way, when I fill up my lone pairs here, all right, that gives me the Lewis structure for beryllium chloride. Notice beryllium only has 2 electrons around it. It doesn't have any more because it's used both of those electrons in making those bonds. It's still a valid Lewis structure though. And if you were to calculate your formal charges of each of these 3 atoms, chlorine, 7 valence electrons minus 1 bond plus 6 lone pair electrons. Each boron has a formal charge of 0. Beryllium, on the other hand, 2 valence electrons minus 2 bonds, 0 lone pair electrons, also 0. There is the argument that, well, why can't we just do something like this? Why can't I just do that and put double bonds to each chlorine? Because then that gives me my 4 bonds to beryllium. And 2, 4, 6, 8, 10, 12, 14, 16, I haven't gone wrong in my number of electrons I'm supposed to use. Well, this is perfectly fine in terms of the octet rule, but when you look at the formal charges, beryllium 2 valence electrons minus 4 bonds, 0 lone pairs, formal charge of minus 2. Not happy. Chlorine, 7 valence electrons minus 2 bonds plus 4 lone pair electrons equals 1. Now, do you remember from the previous video, the most stable Lewis structure is the one that has the least spread out of formal charges. Therefore, although this one is a valid Lewis structure, it's not all that likely because it's not very stable. Anyway, what about though when we get to molecules who can disobey the octet rule by having more than 8 electrons around them? Let me just give you a little bit of a rationale behind how this works. All right, imagine that we have a grape. There's my wonderful rendition of a grape. There is an orange, and here is a grapefruit. And we're going to compare this to relative sizes of atoms. All right, so let's say this is our let's say that's carbon. Let's say that is what should we say? Let's say that is phosphorus, and that is, say, chlorine, for example. In each case, we are getting bigger. All right. You know, perhaps I should change these a little bit just to really emphasize the difference in size. Let's say this one is, let's say that's chlorine, and that's much bigger. Let's say that's iodine. Now, the question I would say to you, if that was a grape, that's an orange, and that's a what did I say? What did I say? I said it was a grapefruit. And you take that grape and you try and take 8 toothpicks and put 8 toothpicks around there. You can probably do it, but they're all going to be really close packed in together. Looking at the chlorine with an orange, it's a lot easier to get 8 toothpicks on there. In fact, you can fit a lot more. Iodine, it's so big, you can put a whole bunch more, you can put a whole bunch more toothpicks on there. So the idea being, the bigger the atom, the more easy it is to disobey the octet rule. Now, it turns out most atoms don't disobey the octet rule by much, but some do disobey it, and sulfur is one of those examples. So what I'd like to do is just to show you what exactly I'm talking about here. So let's look at sulfuric acid, H2SO4. Hydrogen, 1 valence electron, and there's 2 of those. Sulfur is in group 6, 6 valence electrons. Oxygen is in group 6, and there's 4 of those. 24, 30, 32 valence electrons in total. All right. Now, when we think about the central atom, obviously it's not hydrogen. Oxygen is in group 6. 2 bonds it forms, usually. Sulfur is also in group 6, 2 bonds it usually forms. But sulfur is bigger than oxygen. So therefore, more than likely, simply by default, sulfur is going to be the central atom because it's bigger and it has the high likelihood of forming more bonds. Plus, there's the fact there's only 1 sulfur and 4 oxygens, so it just makes sense. Sulfur is probably going to be central. So here's our sulfur. Now, we know that our 4 oxygens have to some way be around the oxygen. So I'm going to do something like this. And we also know the hydrogens have to be somewhere around the outside of the molecule. So that means either attached to the oxygens or to the sulfur. All right? And we're going to look at, well, what if the hydrogens are attached to an oxygen, let's say. Let's say, for example, we have a hydrogen attached here, and I'm going to put one down here as well. It doesn't matter, I put them on opposite sides, that's just what I chose to do. What I would like to do is to come up with the Lewis structure here based on the fact we are trying to not disobey the octet rule. Alright, so let's come up with the Lewis structure. In order for us to not disobey the octet rule, we have to keep 4 bonds to sulfur, so 8 electrons. And that's fine. But if we keep 4 bonds to sulfur, we cannot put 2 bonds to oxygen. So that means that these 2 oxygens need 3 lone pairs, which also means they're going to have a formal charge that they don't want, because oxygen usually likes 2 bonds. And when I fill in the lone pairs for the oxygens that do have 2 bonds, we get a system that looks like this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons from the lone pairs, 22, 24, 26, 28, 30, 32 electrons total. Alright, so my Lewis structure here is fine, it's valid, but we're going to find out it's not particularly happy when we look at the formal charges. Let's look at this oxygen first. In fact, we've seen an oxygen like this before. We saw it in a previous video. Oxygen likes to have 2 bonds. This oxygen only has 1. It's got 6 valence electrons minus 1 bond to the oxygen plus 6 lone pair electrons, giving us a total of minus 1, which means this oxygen has a minus 1 formal charge. Which means this oxygen also has a minus 1 formal charge. Now notice there's no overall charge in the sulfuric acid here, which means all the formal charges must add up to 0. Meaning there's got to be something with a formal charge of plus 2 to somehow add up to 0. The only atom we haven't looked at so far is sulfur. Sulfur itself is in group 6, minus 4 bonds to the sulfur, no lone pair electrons, giving us a formal charge of plus 2. So whilst this is a valid Lewis structure, it's just not very happy. So what can we do? What can we do? Well, I'm going to draw the same thing out again. But I'm going to show exactly the same connectivity. But we're going to talk about something that is going to enable us to reduce our formal charges. Sulfur. It's a period 3 element. Alright? A period 3 element has extra orbitals that you can funnel electrons into. Alright, and what I mean by that, sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Alright. Now from our study of quantum numbers that we saw before, an n value of 3 gives us the possibility of having s orbitals, p orbitals, and d orbitals. Now the d orbitals on the sulfur here have no electrons in them, but they are there. And what that means is the sulfur can accept electrons from somewhere else, in this case from the oxygens, and put them into some of its vacant orbitals. Now we're not going to represent that in an electron configuration in any way. I just want you to understand that it's for that reason that sulfur and atoms bigger than sulfur, although we're only really concerned ourselves with phosphorus and sulfur right now. Phosphorus and sulfur can both disobey the octet rule by going further. Because sulfur is bigger than phosphorus, sulfur can actually accept up to 12 electrons around it. Phosphorus is slightly smaller, it can accept up to 10 electrons around it. Anyway, this is sulfur we're talking about. So what this means is sulfur can actually accept up to 12 electrons around it. Currently it has 8. And if I want to get rid of these 2 formal charges on the oxygens, then the only way to do that is to give myself 2 double bonds. Because then I give my oxygens formal charges of 0. But that looks like it's going to screw up the sulfur. But actually you'll see that when we do that, it doesn't screw it up at all. It actually makes it happier, surprisingly. The oxygens we now know all have formal charges of 0. And if all the oxygens have formal charges of 0, the hydrogens aren't going to change. And if sulfuric acid is overall 0 charged, then that must mean that the formal charge of sulfur is also 0. But let's check. 6 valence electrons minus 6 bonds to it plus 0 lone pair electrons is 0. 0, 0, and 0. All because sulfur is big enough to expand its octet, use those d orbitals, and give itself 2 extra bonds. Give itself those 6 electrons around it, neutralize out all the formal charges, make the molecule that much happier. So, like I said, the goal of the video is to understand that exceptions to the octet rule do occur for atoms bigger than, or atoms in period 3, usually starting off in phosphorus. Phosphorus, sulfur, and anything bigger than that. Anyway, there we go. Thank you.